In part 2 of lecture 2, we will discuss the operating system and external storage. As we saw earlier, computers are connected to their various peripheral devices through a collection of device controllers. These controllers work semi-independently and in collaboration with the CPU to perform whatever input and output operations that the computer needs. Generally, each controller controls a different type of device, but each controller may control more than one device. For example, a SCSI or CSCI controller can control 7 different devices. A device controller maintains its own memory buffer or data and has a set of registers that store commands given to it by the CPU and also status information. For example, the NEC PD765 disk controller has a 16 command language using 1 to 9 bytes in a device register. Its command language includes commands for reading and writing data, moving the disk arm, and formatting tracks. It can even reinitialize, calibrating, and resetting itself and its drives. The CPU starts an input-output operation by loading all the relevant information into the registers of the device controller. This can include the command, the number of blocks of data to be transferred, as well as the direction of the transfer, to the disk or from the disk, for example. If the operation requires moving a disk drive's read-write arm into the proper position first, this may involve more than one step. And after each of these steps, the operating system will have to take over control again, determine what must be done next, and then load new values into the controller's registers. In either case, the operating system will eventually start an input or output operation, which will take a large amount of time compared to what CPU operations typically take. Input and output take much longer than CPU operations, so the computer can do one of two things: wait for the disk drive, or whatever device it may be, to finish or go on and work on something else while it is waiting. When the operating system waits for the device to finish, we call this synchronous I/O because it is synchronized with the operation of the CPU. If the operating system puts that job on hold and starts working on something else, we call this asynchronous I/O because there is no synchronization between input-output and the CPU. Synchronous input-output involves starting the input-output operation and waiting while the data transfer takes place. Many computer systems have a special wait instruction that will keep the CPU idle until the next interrupt is signaled. For those that do not have this kind of instruction, we can write a loop that will keep the CPU spinning its wheels, so to speak, until the next interrupt. There is a real-life analogy to this. Imagine you are trying to get some work done, but you wanted a cup of tea. You put the kettle on the stove and sit there and wait until the water boiled. Obviously, this is not the most efficient way to do this, because you couldn't really get anything else done until you finally saw steam come out of the kettle's spout. Asynchronous input-output is a lot like buying a tea kettle with a whistle. You can get back to work confident that you'll know when the water has boiled because you'll hear the tea kettle whistling. The whistle of the tea kettle is a lot like the interrupt signaling the CPU. Because you aren't waiting for the water in the tea kettle to boil, you can get a lot of other things done in that time. Asynchronous input-output effectively breaks down the job of performing input-output into two distinct jobs: setting up the input-output operation and finishing the input-output operation. The time in the middle can be used by other jobs. This is what makes multi-programming possible. Imagine that you are transferring data through a high-speed modem connection. If the operating system's attention were required for processing each individual character received through the modem, the CPU would not have enough time for the computing needs of application programs. It would spend all its time transferring control to interrupt procedures, transferring the character received, and then restoring the application programs in just enough time to process the next interrupt. Clearly, this is not the best way to handle terminal I/O. Direct memory access allows device controllers to transfer data directly from the device to main memory buffers. This is particularly important for high-speed devices such as disk drives. Now, data is transferred a block at a time, which makes for much more effective use of the CPU's time. Direct memory access requires a special controller, which allows the device controllers to access memory without going through the CPU. It is another example of how operating system design is a strong influence on the design of computer hardware. One thing that has remained true about computers since the early days of the UNIVAC is that disk storage is much cheaper than main memory. As a matter of fact, it has usually been 3 orders of magnitude cheaper. Even if we could cram all the memory that we would ever need inside a computer, this would make the computer far more expensive than anyone could possibly afford. Also, the circuits that are used to store computer programs are volatile, meaning that when the computer's power is turned off, the contents of memory is lost until we save it on some external storage medium. For these reasons, external storage has been used on computer systems from the very start. Since computers never have as much memory as programmers and users wish they had, its programming is stored on disk, as well as data that is not in immediate use. External storage is much cheaper than memory, but it is also much less convenient. It takes time to load programs into memory, and it takes time to read data from files. But without external storage, the data capacity of computer systems would be a fraction of what they are now. The only storage that the CPU can access directly is its own registers and main memory. All others are performed using the services of the device controllers. Sometimes we can make it more convenient and faster by the use of memory-mapped I/O. We set aside a series of addresses and assign them to various controllers and ports. We can now access the data held in these locations by the use of regular move instructions. The end result is a fast response time. The IBM PC uses this approach for managing video display. Each screen location corresponds to a specific byte of memory. Displaying data is as easy as moving data to a particular part of main memory. Imagine that your computer is transmitting data to the printer through its parallel port. This kind of operation typically happens 1 byte at a time. After the byte starts transmitting, the CPU will continue to check the status bit to see when the operation is completed. The continual checking of the status bit is called polling. This is an example of programmed I/O. If the CPU were to simply wait for the device to signal an interrupt, it would be an example of interrupt-driven input-output.